all that is good here, so I won't make any more loud clicks on my keyboard. So I started thinking about this talk maybe about 2 months ago or something. This is a direct response to discussion of American climate policy after the passage of the Inflation Reduction Act, which is Joe Biden's big climate bill that passed in August. And I think many commentators are either lying on purpose or don't know very much about climate science in the way that they talk about American climate policy. And I think one thing that's really lacking is being honest about our historical emissions and about what we've done in the past. And I think that's a thing that's really getting in the way of true climate progress. And so to attempt to make that progress and to attempt to tell the story of climate science and historical emissions and climate action, this is my attempt at telling that story. So this is split into 5 components. An introduction about why carbon dioxide matters so much. And then we'll get into the meat of the science. We'll talk about the ocean, how it's slow, and why that matters so much for our emissions and the way that we impact the climate. And then we will talk about carbon accounting, how carbon emissions are counted between countries in the present and in the past, and how future carbon emissions might be doled out to deserving countries. And then I'll spend a little bit of time just talking about why I think American climate action is kind of empty in a lot of ways. And then in the conclusions, I'll talk about how this sets the stage for next week when the big climate conference will happen in Cairo, Conference of Parties 27, which you may have heard about. It's going to be a big deal. So talk about global warming, you have to talk about Earth's energy balance. Everything on Earth with the climate system starts with the sun. So if you start the top left of this figure, energy comes into the climate system, and some of it is bounced away by clouds or dust in the air. Some of it is reflected by bright things on the surface, things like snow or sand, things that are bright. So about on average, 30% of sunlight is reflected away from Earth's surface, and this is called the albedo of the planet, about 30%. The remaining 70% is absorbed by the atmosphere and by the surface of the planet, by the ocean and by land. So everything is heated up, and since we're warm, we emit infrared radiation. So that's the wavelength that we all emit in. I'm emitting it right now. You're emitting it right now. The place where you're sitting or walking around, all the things near you are emitting infrared radiation. And so that's what's shown in the middle of this graphic, the big fat red arrow going towards space. So infrared radiation, it goes out towards space. And if we didn't have an atmosphere, and more importantly, if we didn't have greenhouse gases, all of that infrared radiation would escape into space. But it turns out that we do have greenhouse gases. And the special property of greenhouse gases is that they're able to see infrared radiation. So greenhouse gases are invisible to visible light, but they're able to see infrared radiation, and they absorb infrared radiation and they heat up, and then they re-emit radiation up and down. And so if you look at the third big arrow, the back radiation, that is what greenhouse gases do for us. It traps some of that radiation before it escapes to space, and it sends it back down to us. And that's what makes life on Earth possible. So greenhouse gases really make life on Earth possible. But the problem is if you look at the middle arrow again, you can see that not all of it gets absorbed by greenhouse gases. There's this thin red section of the arrow that goes directly to space. And this is called the atmospheric window. And so this is a piece of the infrared spectrum that slides past greenhouse gases. It's invisible to greenhouse gases. So what happens is we add more greenhouse gases to the atmosphere, as we add more carbon dioxide, methane, nitrous oxide, fluorinated gases, it fills up the atmospheric window, and less infrared radiation that used to slide past the greenhouse gases is able to and escape to space. So basically there's less outgoing radiation than there used to be, denoted by the negative in this slide, and there's more radiation staying within the climate system, not escaping to space. So we're closing the atmospheric window, and we're allowing less radiation to escape to space than we did in the past. And that means that the climate system heats up. So the most important place to us where this extra heat goes is into the atmosphere. So this is a record from 1850 through the present of change in global average near surface temperature, 2-meter air temperatures. And you can see a gradual rise in temperatures through the middle of last century and a much faster rise since the to the present. And so currently we're at about 1.2 or 1.3 C above the 1850 to 1900 average before global warming really took over. And it seems like this year is maybe going to be about the 5th warmest year on record. And the warmest years on record are still 2016 and 2020. The things that made 2016 and 2020 unique is that they were El Nino years. So in El Nino years, there's much more warm water that sloshes over from the West Pacific into towards the Central and East Pacific. And that exposes much more warm water to the atmosphere. So the atmosphere gets warmer. But right now we're in a triple dip La Nina. We've had kind of a La Nina 3 years in a row, 3 winters in a row. And so that means that there's extra cold water exposed to the air. So that kind of dampens the global warming signal. This is natural variability on top of the man-made signal of global warming. So you get a little bit of noise on there. And it's likely that in the next 3 or 4 years, we'll have another El Nino. And that will help us set our highest temperature record. Maybe we'll get up to about 1.4 or even close to 1.5 C above pre-industrial temperatures during the next El Nino just passing. But if you're going to talk about global warming, you can't just talk about air temperature. You have to talk about the ocean. And this graphic really demonstrates why. So this graphic shows where all of the extra heat that we've trapped in the climate system has gone over the last 60 years. And so there's a few colors here. You can see all the blue colors are different depths of the ocean. So tons of extra heat have gone into the ocean, and particularly the top ocean, the top kilometer of the ocean, and less has gone into the deeper parts of the ocean, the darker blues. But on average, about 90% of the extra heat that we trapped in the climate system stays in the ocean. So really, if you talk about global warming, you're talking about heat piling up in the ocean. And if you look at the other parts of the climate system, in gray is ice, what climate scientists call the cryosphere. So this is, the ice sheets over Greenland and Antarctica, Arctic sea ice, Antarctic sea ice. And basically it takes energy to convert that ice into water to melt it. And that's what this gray shows. It shows the melting of ice. And so as that ice disappears, it takes energy to turn it into liquid water. The land takes up heat as well, particularly in Arctic regions, places with permafrost that's shown in orange. And that tiny purple sliver is the atmosphere, the thing we care about the most. And so the thing that I like to emphasize about this is that global warming would be much, much faster and much, much harsher if we did not have ocean covering most of the planet, right? Water has a very high specific heat. It can absorb a lot of heat without warming up too much as compared to the land surface in particular. And so the ocean sort of acts as a dampener on global warming. But that has, sort of a bad side to it as well. And that's what I'm going to talk about in the second section. So the ocean acts to slow down global warming, but it also, unfortunately, gives the climate system a lot of memory, and it drags out the signal of global warming far into the future. So a big thing that people talk about and think about a lot is which greenhouse gas is most important. So this is a really hard kind of question to answer because all greenhouse gases have different properties. And so some of the key properties that you have to think about with every greenhouse gas is on a per ton basis, how much warming does it generate? How much heat does it trap in the climate system relative to the same amount of CO2? That's called the global warming potential. And it's usually measured over a standard amount of time. You'll either see 20 years or 100 years. I've used 100 years here. And you also need to know how long it lives in the atmosphere. So its lifetime. So from the time it's put into the atmosphere to the time it's removed from the atmosphere to the time it's important to the radiation balance of the climate system. You also need to know the size of its sources and its sinks. How quickly is it piling up in the atmosphere? And so if you can combine all three of those things, you can get a sense for which one is most important. So let's just compare them qualitatively here in this graphic. So the one that a lot of people are thinking about these days, methane, it's a very strong greenhouse gas. It has a GWP of 28, so it warms 28 times more than the same amount of CO2 over 100 years. But it only lasts in the atmosphere for about a decade. It reacts with a hydroxyl radical. And so that processes it quite quickly out of the atmosphere. There's a small sink with soil microbes that eat methane as well, but for the most part, it's the hydroxyl radical. And it comes from anaerobic decomposition in wet places, right? Like wetlands is the big natural source. And we produce it from leaks in the production of oil and gas, livestock burps, cow burps, the cultivation of rice paddies because they're flooded, and landfills as well. They all can produce methane. A second important one, particularly for agriculture, is nitrous oxide. Its 100-year global warming potential is 265. So over 100 years, it's 265 times more effective as a greenhouse gas than the same amount of CO2. And it lasts in the atmosphere about 120 years. And so it comes from nitrogen in soils, both as a natural source, but also because we add fertilizer to soils. It comes from manure, it comes from fossil fuel combustion, and it has some industrial sources as well. The big one, though, is fertilizer. And then it's broken down by UV radiation in the stratosphere. So that's why it lasts so long, because it takes a while for stuff to break through to the stratosphere from our part of the atmosphere. A tricky one to talk about is fluorinated gases. So this is a whole family of gases. They're mostly CFCs, which have been phased out under the Montreal Protocol in all of their replacement gases. And there's a whole family of them, HCFCs and others like that. And these all have different warming potentials. They all have different lifetimes. They span a warming potential from 10 all the way up to 20,000. Times stronger than the same amount of CO2. So some of these are very, very effective greenhouse gases. And some of them take a really long time to leave the atmosphere, because a lot of them are only made by man-made processes. So they can stick around a long time. So some will stick around for more than 10,000 years in the atmosphere. So they come from refrigerant leaks. This is the stuff that's used as refrigerant. And then there's some things like sulfur hexafluoride, which is used in industrial applications, which is also a very strong greenhouse gas if it leaks. For the most part, this is broken down by UV radiation in the stratosphere, again, and some reaction with the hydroxyl radical, kind of the detergent of the atmosphere. So they can stick around a very long time, and all of them have pretty different properties. So the big one is carbon dioxide. And so the thing that you'll probably notice is that it, of course, only has a GWP of 1 because you're comparing it to itself, right? And so it's the weakest greenhouse gas on here over 100-year time frame, right? The problem with it is the next part. It's that its lifetime is years to 10,000 plus years. And so that's the problem with CO2, is that it sticks around a really, really long time. The other problem with it is that it's the thing that we emit the most. So CO2 it has a lot of natural sources, decomposition of former living things, volcanoes, wildfires. When deep ocean water comes up, it's often rich in CO2 and it releases CO2 into the air. And then there's all the man-made things, right? Things like cement production produces CO2. Whenever we clear forests and clear wetlands, that produces CO2. And the big one, whenever we burn oil, gas, and coal, that creates CO2 as well. And then the sinks are things like soil, plants, living things on land, living things in the water. The chemistry of the water takes up CO2. That's what controls pH of the water. And silicate rocks also can take up CO2 eventually. So this is why CO2 is so complicated, is because it's removed through a variety of ways. And the slowest way, which is the silicate rocks, is a geologic process. It's something that can take on the order of hundreds of thousands of years. And so this is the problem with CO2. So this is another way to look at a comparison between all of those greenhouse gases. So this is looking at the top of atmosphere radiative imbalance because of the greenhouse gases that we've added. So this is basically looking at the relative importance of those 4 greenhouse gas families that I talked about. So the biggest one by far in teal is carbon dioxide. The next most important one is methane in this kind of pukey green color. Nitrous oxide is in pink. And the fluorinated gases, CFCs, and their replacements are below that, yellow, blue, and orange. So if you wanted to kind of compare them, CO2 is about 2/3 of present day warming at the top of the atmosphere. Methane is about 1/6, and the remaining gases are about 1/6. So CO2 is relatively weak, but we emit a ton of it, gigatons of it, and it builds up in the atmosphere. And so that's the problem with CO2. So key takeaways from this first section. We're at about 1.3 C warming, and about 90% of the extra energy trapped by our added greenhouse gases has gone into the ocean. Global warming would be much more rapid without a global ocean absorbing heat. All greenhouse gases are important, but we can compare them by comparing their ton-to-ton warming strength, this global warming potential, their average residence time in the atmosphere, how long they survive in the atmosphere, and the size of their sources and sinks. So you'll often see something called CO2 equivalent emissions, CO2 EQ. And so what this tries to do over either a 20-year or 100-year time frame is it lumps all greenhouse gases together. Oftentimes you'll see, trying to summarize all greenhouse emissions into one number, the CO2 equivalent. But I personally really don't like that. You kind of have to choose to use it because that's what a lot of people use. But as I argued in these couple of slides here, every greenhouse gas is very different, and in particular, their lifetimes in the atmosphere are very, very different. Each greenhouse gas is important, and I think they all have to be considered differently because they all have different impacts, different sources and sinks, and different lifetimes. So if you summarize, we emit so much of it and it sticks around in the atmosphere for so long. Carbon dioxide is responsible for about 2/3 of present-day warming, methane about 1/6, and nitrous oxide and the fluorinated gases about the remaining 1/6. So, 66% or so of present-day warming is caused by carbon dioxide. It's not only the most important greenhouse gas today, it's the most important greenhouse gas far, far into the future. And so we're going to discuss why in the next section. So this section talks about the slow ocean. And so this is a cool demonstration of just how slow the ocean is. This is a summary of a whole bunch of ocean-going research vessel transects. And what they did on these transects is that they measured helium isotopes. And in particular, for this study, they looked at tritium isotopes. So the main reason that there is tritium in the atmosphere and tritium in the ocean is from nuclear bomb testing, from atomic bomb and nuclear bomb testing. And so we put a whole bunch of tritium into the atmosphere between 1945 and 1962. This awful thing that we did. And it turns out that you can measure tritium in ocean water. And so what this is it shows 4 transects of tritium in the Atlantic Ocean, depth versus latitude, so north-south and how deep it is, along this red line in the bottom right-hand corner of the graphic. So this is a research vessel transect that goes from Newfoundland to Suriname through the North Atlantic. And so after the Test Ban Treaty was signed in 1963, we stopped putting tritium into the atmosphere. And 20 years later, this is where tritium was measured at the top right graphic here. It was only measured in really the top 500 meters or so of the ocean, except in the far north. As you go 15 years later, in 1997, it started to mix down a little bit. This tritium that last would have been put in the atmosphere 35 years ago. Go 6 years in the future, it mixes down a little bit more. Go another 9 years in the future, 50 years after the Test Ban Treaty was signed, and you get a little bit more mixing down into the deeper ocean. So this is a demonstration of just how slow the ocean is. So on the right-hand side of this graphic, which is the northern Atlantic, what happens in the northern Atlantic is the creation of something called North Atlantic deep water. So really cold air blows off the Canadian Arctic into the Labrador Sea, and I think to a smaller extent off of Greenland into the Arctic Ocean. And it cools down the water really rapidly. And cold water is very dense and it sinks very efficiently down. And so that's what's being shown here is these cold parcels of water being shot down into the deep ocean in the North Atlantic. But you can see, even with this relatively fast part of the ocean, you can see a huge part. If you look in the 2012 graph at the bottom, more than half of the ocean really hasn't experienced any of this tritium that went into the ocean. So this part of the ocean where it mixes very efficiently in the North Atlantic, the cold places where the cold water is made, gets to see some of the tritium, but there's huge parts of the ocean that haven't experienced it. And this is how heat and lots of carbon reach the deep ocean, through these slow pathways. And this is demonstrated even better in this next graphic here. So this shows what oceanographers call the age of ocean water. So the age of ocean water is the last time a chunk of the ocean has been exposed to the air. So the last time it's been ventilated. And let's start with the middle graphic here, which shows the same picture that we were seeing in the last graphic, but expanded to the southern hemisphere. So we're looking at latitude versus depth of the Atlantic Ocean, and we're looking now at the age, the last time it has seen the surface. So you can see that there's two places where the water is very young, in the North Atlantic, where North Atlantic deep water is made, and in the far southern Atlantic near Antarctica, where what's called Antarctic bottom water is created. So in the Weddell Sea near Antarctica, it's extremely cold. And you have a place where the very, very cold air runs over the ocean, and it creates this extremely deep water that goes flying down all the way to the bottom of the ocean, even deeper than North Atlantic deep water. And you can see that, just how far down this Antarctic bottom water goes in the far southern Atlantic. So you can see in the North Atlantic and the South Atlantic, you have places where the water is very young. It has seen the surface and the surface conditions in recent years. But in the middle of the Atlantic, in the tropical Atlantic and the subtropical Atlantic, you have pretty old water. You have water that hasn't been to the surface in 500 or more years. And that's even more dramatic if we go to the Pacific on the right. So this shows the Pacific Ocean, another cross-section, which is north-south along the x-axis, and depth along the y-axis, going down to the bottom of the ocean. And you can see that the Pacific is much less dynamically active than the Atlantic. It doesn't have a place where deep water is formed in the same way the Atlantic does. And because of that, it has very, very old water. So all of this yellow-orange water hasn't been to the surface in 1,000 or more years. And the reddest place hasn't seen the surface in maybe 1,500 years or so. So there's very, very old water, very, relatively stagnant water that hasn't experienced what the surface is saying. And you can see on the left, there's a latitude, longitude one, kind of looking from above, of the average age of deep ocean water, from 1,500 meters below the surface down to the bottom of the ocean. And you can see that the Atlantic is relatively young. It's a dynamically active ocean. You can see the Indian Ocean has pretty old water. A lot of the water is on the order of 500, 600, 700 years old. But the Pacific is very old. It's not very dynamic. So there's a lot of really old water, particularly in the North Pacific, where a lot of the water has not seen the surface in the deep North Pacific in more than 1,000 years. So why does this matter for our carbon emissions? Why does this matter for the science of global warming? Because these ocean waters, these really deep and old ocean waters, they have no knowledge of global warming, right? So when this ocean water surfaces in 500 years or something, and it sees that there's this huge imbalance in energy at the surface, it has to warm up. The whole ocean has to warm up to come to equilibrium with the radiative imbalance at the top of the atmosphere. So you have all of this ocean water that has no knowledge of global warming. And so constantly this ocean water is coming up, and it's so old, and it has no knowledge of global warming, and it's so cold as well. And so this is this huge drag on global warming. So the ocean acts to slow down global warming because it's always bringing this cold ocean water up. Ocean water, absorbs a lot of heat before it increases its temperature significantly. But that also increases the tail of global warming because it takes a very, very long time, more than 1,000 years, for the ocean to come to equilibrium with surface climate conditions. And that's what's shown here by the age of the ocean water. You can see there's huge parts of the global ocean that are not going to see the surface conditions for more than 1,000 years. So what is the implication of this for global warming and the next, kind of 100 years of climate action? So let's step back and look at CO2 sources and sinks. So this is a graphic from the Global Carbon Project, which will have its update next week on November 11th, which is it's a very nice update. Everybody should follow them. And there's two things that are at the top of the graph here. There's two big emissions from human sources. There's land use change in beige. So that's clearing forests, that's clearing wetlands, draining wetlands, and that puts CO2 into the atmosphere. The other one is the gray, and that's the big one, and that's burning fossil fuels, oil, gas, and coal. And so that's the main one. At the beginning, clearing forests was more significant a long time ago, but then we started burning fossil fuels in earnest, and that became much more important. So where does the CO2 that we emit go? So we're emitting about 40 gigatons of CO2 a year. Where is it all going? And so that's what's shown on the bottom of the graph. The ocean absorbs about 25% in a given year. The land surface absorbs another 25% in a given year. And the atmosphere retains about half. So the land and the ocean are able to take up about half of what we put into the atmosphere, and the rest of it stays and elevates atmospheric levels. So we keep dumping CO2 in, and about half of it stays in the atmosphere. So what does this CO2 look like on kind of a geologic timescale? How does the ocean, the very slow ocean, and even slower processes perceive all this CO2 that we're adding in the last 250 years and really in the last 100 years or so? And so to kind of look at just how fast we're adding CO2, we're going to go back farther in the climate record. So this is looking at ice core records of CO2 going back 800,000 years. And so this is looking at ice core records of Greenland. And what you do is you take a core of ice of the Greenland ice sheet, and you go down and you carefully take a core out. And if you're able to date the ice and find out how old it is, you can find little bubbles of trapped air that are from that time period. And so, and you can measure the CO2 and other atmospheric components in that little bubble of air. And so that tells you what the atmosphere was like, hundreds of thousands of years ago. And so that's what's plotted here. So you can see this up-down pattern on the graphic here. And when CO2 was relatively high, Earth was relatively warm. When CO2 was low, Earth was relatively cold. And ice probably would have been covering where I am right now, and probably where a lot of you are as well. So Earth bounced between ice ages and interglacial times, warm and relatively cold times. So let's go all the way to the right, the far right-hand side of the graphic here. And we can see this little leveling out of CO2. So this is the last 10,000 years, and this is called the Holocene. So this is the sort of climatic period where CO2 was quite stable, where climate was quite stable. And the fact that climate was stable is what allowed complex societies to evolve. It's what allowed us to develop agriculture. It what allowed us to have, cities and complex cultures. So the thing that we're kind of doing now is, if you keep going all the way to the far right-hand side of the graphic, is we're throwing away that stable climate, right? So in the past, if you planted crops, you had a good guess that they were going to work because you knew that you had planted crops the year before, or your parents did, your grandparents did. You had some continuity in the climate. You had confidence in what you planted, but we're throwing that stability away, and that's demonstrated on the far right-hand side of it. So this is direct observations of CO2 in the atmosphere matched to the ice core record. And you can see that we're adding CO2 to the atmosphere so fast, it's essentially a vertical line, right, compared to previous changes. So we're just dumping CO2 into the atmosphere, possibly at one of the fastest rates that have happened in Earth's climate history. So this kind of acts as a massive pulse of CO2 into the climate system, because it's being added much, much faster than the ocean can react to it. So it acts as this massive pulse. So what happens to this huge pulse of CO2 in the climate system? So this is a graphic from the IPCC, and it shows where this huge pulse of carbon goes over 3 time periods: the first 100 years, through 1,000 years, and through 10,000 years. So let's start on the left. So in the first 100 years or so, land processes act to take up CO2, and the upper ocean acts to take up CO2. So the chemistry of the ocean takes up CO2, and that increases that changes the pH of the ocean as it absorbs more and more CO2. But the upper ocean gets exhausted, and the upper ocean becomes less efficient at taking up CO2. And so then this time scale I was talking about, where very old water takes more than 1,000 years to reach the surface, comes into play. And so the second thing, what the IPCC called ocean invasion, is this upper ocean that's kind of run out of ability to take up CO2, starts to mix with the deep ocean, and the deep ocean starts to help absorb CO2. And so this is a process that takes, kind of like 1,000 years or so, because that's how slow the ocean is, this communication between the upper and the deep ocean. And then as we get into the sort of even farther than 1,000 years, there's this recalcitrant chunk of carbon left in the atmosphere. And this actually is not removed by the ocean. It's removed by weathering. So this is a reaction with silicate rocks. So raindrops are exposed to the high CO2 in the atmosphere. And so rain combines with CO2 in the atmosphere to form carbonic acid. And that falls on silicate rocks. And that combines with silicate rocks, and it removes the CO2 from the water. And that forms, and it weathers it. So you get this CO2 weathering in the reaction between carbonic acid and silicate rocks. And this process takes on the order of 100,000 to 1 million years or more, because this is how the geologic carbon cycle works. The geologic carbon cycle is a balance between volcanoes emitting tiny amounts of CO2 and weathering removing tiny amounts of CO2. And that's a process that can take millions of years to come to equilibrium. So the fast part of the time scale is kind of land surfaces in the upper ocean. The middle part of the time scale is the slow ocean. And the end of it, the part that takes tens of thousands and hundreds of thousands of millions of years, is this geologic component of the carbon cycle, this geologic sink. So you can see that even after 10,000 years, there's a significant amount of CO2 left, and the amount that's left is dependent on how big the pulse is, which is what's shown on the right-hand side. Currently, we've emitted about 700 petagrams of carbon, so we're somewhere between the blue line and the yellow line, but we're nowhere close to the red line, and we probably will not be able to emit that much. It would take a heroic effort to emit that much as the world warms to keep society together. And a geochemist, David Archer, has a really nice quote that I always like to say when I talk about this graphic and I talk about the lifetime of CO2, which is that the average of lifetime of atmospheric CO2 is 300 years plus 25% that lasts forever. And he's trying to summarize all of these complex processes that remove CO2 from the air. So, the 300 years is mostly the ocean being slow, and what he says 25%, what the IPCC calls 15 or 20%, is this part that's removed by the geologic carbon cycle. So CO2 is removed by many processes, and it sticks around a really, really long time because of that. So what happens because CO2 sticks around for so long? Because CO2 sticks around for so long, its warming sticks around for so long. And that's what this graphic shows. So this graphic shows a comparison between the two big greenhouse gases that human activity emits, CO2 and methane. And this is really nice graphic. It shows a comparison of 1 year of methane warming versus 1 year of CO2 emissions warming. And so the methane is shown in red, and you can see the methane warming is very significant, right? But because it's removed from the atmosphere very quickly, its average lifetime is only about 10 years. Its warming effect fades away very, very quickly. And it's almost gone after a few years. The ocean gives it a little bit of memory, as you can see, but it peaks almost right away, and it starts to tail off almost right away. And that's because it is destroyed by the hydroxyl radical in the atmosphere, which is a very efficient way to kind of remove pollutants from the atmosphere. It's what keeps a lot of things clean in the atmosphere. So that is in comparison to CO2. So methane has gone pretty quickly. CO2 has not gone quickly at all. And that's because it is removed by these very, very slow processes, the ocean processes and the geologic processes. And so it has a very, very long tail. And you can see it takes 10 or 20 years to reach its peak warming. And once it's reached its peak warming, it's there, for more than 100 years. And so this is the key fact about CO2, is that its warming is around for a very, very long time. And that is mainly true because the ocean is so slow. It takes the ocean so long to come into equilibrium with current climate conditions. So what's another way of looking at that? So this is from a paper from Susan Solomon and co-authors from about 15 years ago. And this looks at sort of our impact in the long term. So they looked at climate change in a simple climate model out to the year 3000. And they did a very simple experiment. They just increased CO2 up to a given threshold, 450, 550, 650 ppm, and so on. So we're at about 420 ppm. I don't think we're going to get much farther than 550 personally. I just don't think we can keep it together that long to get our emissions that high. And so I think we can just stay on the lower part of this graph. So let's track what happens when we go up to 550. So you can see as we go up to 550 and we stop emitting, CO2 emissions start to tail off, or CO2 in the atmosphere starts to tail off. Emissions go to zero, so concentrations start to drop, right? So you can see that these fast ocean processes and these slow ocean processes start to remove CO2 from the atmosphere. And they do quickly at first, and then they lose efficacy going forward. And so you can see that even 1,000 years into the future, CO2 in the atmosphere plateaus well above the baseline of 280 parts per million, the dashed line at the bottom. So what does this mean for temperature? As the ocean comes to equilibrium with the CO2 that's in the atmosphere, the warming does not go away. So if we track the temperature line here, we go up to the second line. So this is about 2 Celsius warming above pre-industrial, and we stop emitting. You can see that temperatures after a little bit drop a little bit, and after 1,000 years they maybe dropped about 0.2 degrees C or so. But this demonstrates a really fundamental thing about CO2. Because CO2 sticks in the air for so long, kind of the temperature that you're at when you achieve net zero is the temperature of the climate system for a really long time, hundreds of years, if not centuries. So we're at about 1.3 C right now. That's probably the temperature that Earth is going to have, for 1,000 years or more. That's what this is saying. And the only thing that would kind of undo that is if we somehow invent really cheap carbon dioxide removal, and we get to it quickly, and we do it on an enormous scale, a scale that's inconceivable at this moment with the state of that technology. So the warming that you sort of get to net zero at is the warming that you're committed to for centuries, if not longer. And that is a result of the fact that CO2's warming has a very, very long tail, as we saw in the previous graphic. So the thing that you can see, the fact that CO2 has such a long tail, means that the effects of CO2 are cumulative. CO2 emissions from the 1800s are as important as CO2 emissions today. And so that is shown in this very, very nice graphic from the IPCC. On the x-axis is shown cumulative emissions, how much we've emitted in total since 1850. And on the y-axis is shown temperature above pre-industrial. So you can see historic warming and emissions are shown by the dark black line and the gray shading. And future possible pathways of warming are shown in the colors there, the teal and the oranges and the rose. And basically what you can see is that they have an almost linear relationship. The more CO2 emit, the more warming you get. So what you can do is you can look at the left-hand side of the figure and say, okay, I want to keep warming below 1.5 C. Then you can bring your eye across the figure, and you can go and you can find the line that shows the relationship between cumulative CO2 and temperature. And you can see just how much cumulative CO2 can be emitted before you probably breach 1.5 C. And so on this graphic, that's about 3,000 gigatons of CO2 total, which would be about 500 more gigatons or so. And this graphic, I think, was made a few years ago, so that's already out of date. But this tells us, this concept is called the carbon budget. How much more CO2 you can emit before you pass a key warming threshold. And the reason you can do that is because the effects of CO2 are cumulative. Emissions from 10 years ago, 20 years ago, and 100 years ago are as important as CO2 emissions today. They add up. So that brings me to the takeaways of this section. So the slow ocean. So in recent years, about 25% of our CO2 emissions are absorbed by the ocean. About 25% are absorbed by plants and soil, and the remaining half elevates atmospheric CO2. In the long run, most of that CO2 will end up in the ocean. And we've added the CO2 so fast, the ocean perceives it as a pulse. The climate system perceives it as a pulse. We've just added it so fast, most of it in less than a century. And this enormous pulse of carbon we've put into the atmosphere slowly works its way into the upper and lower ocean. And that process takes more than 1,000 years. And there's a final stubborn fraction of CO2 that's slowly taken out of the atmosphere by silicate weathering, by the kind of geologic slow part of the carbon cycle. And that process takes tens of thousands, hundreds of thousands, and possibly even millions of years for our CO2 that we've emitted. And so, since the ocean overturning is so slow, this talking between the upper ocean and the deep ocean, and the ocean is the primary removal process of CO2, and most of the deep ocean is still very cold and hasn't been exposed to the warm atmosphere that we've created, the climate effect of added CO2 lasts for millennia. And so that's a direct result of the fact that the ocean is slow, that the ocean takes a long time to communicate from the deep ocean to the top ocean. So again, there's lots of ocean water that hasn't been to the surface in more than 1,000 years, in all ocean basins. And so, since the climate effect of CO2 sticks around for so long, its impact is cumulative. Emissions from the 1800s matter as much as today's emissions. And this is perhaps the single most important takeaway from the science of global warming. And I'm going to talk about why in the next section a little bit more, right? So the impact of CO2 emissions are cumulative. Emissions from 100 years ago matter as much as today. And since cumulative CO2 scales with warming, X more CO2 means Y more warming, we can develop carbon budgets, which are rough estimates of how much carbon is left before key temperature targets are crossed. So a carbon budget. So the next question is, how big of a piece of the remaining carbon budget does each country get? So you can sort of slice up the remaining amount of emissions if you want to stay under a certain temperature target. But then the question becomes, how do you slice up the remaining emissions? So let's step back again and let's look at emissions through today. This is a graphic again from the Global Carbon Project, and this just is look at fossil fuel CO2 emissions, so this does not include land use. And you can see that in the last few years, we've emitted about 36 gigatons of CO2. You can see the COVID dip in 2020, but we bounced back in 2021. And I think we're going to be higher than 2021 and 2022 again as well. But again, the numbers come out next week. So you can see that the only thing that's really slowed down CO2 emissions post-World War II is economic crises. The collapse of the Soviet Union, 2008, global economic crisis, COVID-19, the oil crises. These are the things that slowed emissions down. The hope now, of course, is that renewable technology and non-fossil fuel technology is getting good fast enough that perhaps we can get a dip in emissions, not because because the economy is collapsing. So if you add on land use emissions to this, we're at about 40 gigatons of CO2, as we talked about before. So we're emitting about 40 gigatons of CO2 a year. Most of that is from fossil fuels. So how do you break this down by country? So this shows the top 6 emitting regions and countries. China is the biggest emitter. In the US is the second biggest emitter. Again, this shows data through 2020 when emissions dropped because of COVID. Emissions dropped back, bounced back, I think almost all of that loss. So the US is closer to a little bit above 5 gigatons of CO2 a year, I think in 21 and 22. The EU and India are about 2.5 gigatons a year, Russia 1.5, Japan 1. And so those are the big emitters. And you can see there's a big gap now between the USA and China. You can see China's rapid industrialization in the 2000s when they went from the EU's carbon emissions to well past the US's really in just a matter of 10 years or so. Just rapid industrialization and modernization on the back of coal power. And you can see, though, that if you go back in the past, the US emissions have been high for a long time, and the EU emissions have been high for a long time, along with Russia as well. So China has high emissions now, but it's a very recent development. So, as I argued in the last section, emissions from the 1800s and the 1900s matter as much as emissions today. So that means that if you're going to judge the climate impact of someone's emissions, you need to look at cumulative emissions by country. And that's what this graphic shows. This is from Carbon Brief. And what they did was they looked at the major emitters and they looked at cumulative emissions. And so just to kind of exaggerate the point, I'm looking at fossil emissions and land use emissions. So oil, gas, and coal, as well as land clearing. And you can see that if you look in this format at cumulative emissions, the United States is far and away the biggest emitter. Far and away, not even close. The US is over 500 gigatons of CO2 emissions through 2021, and China is still below 300 gigatons of CO2 emissions. So the US is far and away in first place. On the old version of this graphic, they actually lumped together all of the EU countries, and if you do that, the cumulative emissions are closer to the United States and above China if you lump together the EU countries, but they don't do that anymore. You can see Russia is the third biggest emitter by countries by cumulative emissions. And you start to get into some really complex interpretations of carbon emissions. So you can see that Brazil and Indonesia have really big land use emissions from land clearing of rainforests, clearing from tropical peatlands. And I think you then get into on hard questions that are important to think about. Which is, are citizens of the countries always responsible for emissions that happen within their borders, right? So a lot of the land clearing in Brazil, is for soybeans that are sold internationally, for beef. A lot of the land clearing in Indonesia is for things like palm oil that is also sold internationally. And if it's outside money that caused those emissions to happen, are the local people always the ones responsible or fully responsible? And so I think that those are hard questions that are important to ask. But I think for the major emitters, this is a good metric to use. This is a really good graphic to remember. So something that people always ask when they see this graphic is that, oh yeah, but China industrialized and now they build all of our stuff. So what if you take that into account, the embedded emissions and stuff that we buy from China? And so that's what this graphic looks like. And so this is a difficult thing to do, to adjust emissions for trade. So this is one estimate of it. I don't think it's the final answer on it, but I think the answer to that is really that those embedded emissions aren't quite as big as people perceive. We export a lot of emissions in the stuff that we export, and we import a lot of emissions in the stuff that we import. That gets passed around the world. And so you can see the added CO2 emissions from imports are in red, and the subtracted emissions from exports are in the light gray. And you can see that increases the gap between the US and China. So now the gap is 250 gigatons, or if not more. So if the current gap in annual emissions were held constant, which is about 5.5 to 6 gigatons of CO2 per year, if that gap between the US and China annual emissions was held constant, it would take China more than 40 years to overtake the US as history's biggest emitter. And of course, China has very serious decarbonization plans. It seems like there's a good chance their emissions will start bending down in 2030, if not earlier. And they have a very serious net zero plan in 2060, much more serious than any goal that the US has. And I don't think it's a coincidence that 2060, right? I think there's a good chance that they are trying to keep their cumulative emissions lower than ours. I don't think that's beyond reason. So the US is history's biggest emitter. Cumulative emissions are what the climate system cares about. That means for the foreseeable future, in the next 30 years, when climate damages are at their worst, politically speaking, relative to climate action, the US will always be the one that is most to blame. And this graphic explains why. So you can sort of add up all the historic emissions. And that takes you through the present. You can say, okay, so this many emissions got us to this much warming. How much more can we emit before we pass a key temperature threshold? So this is the carbon budget. So an example of the carbon budget is shown in this graphic. So on the left is two estimates of the carbon budget for a 50% chance of remaining under 1.5 C. And on the right are two estimates for a 66% chance of staying under 1.5 C. And so the new models, which are shown in blue, they actually had better estimates, so it was able to increase the carbon budget a little bit. But both of them demonstrate an important point, which if you want to move from 50% certainty to 66% certainty, the carbon budget shrinks. So less risk requires a smaller carbon budget. And in fact, if we wanted a 100% chance to avoid 1.5 C, we would have actually ended emissions years ago. Right? There's a good chance that we've actually already used up the 1.5 C carbon budget. There's a decent chance. So less risk requires a smaller carbon budget. This is a fundamental rule of carbon budget. So if you ever see a 50% chance carbon budget, that's making it as generous as possible. And if you see a 66% or 75% chance carbon budget, that's the risk averse option, right? So there's one that's friendly to high emitters, and there's one that's friendly to the people that suffer the effects. So always keep an eye on that percent chance that's built into the carbon budget. So the carbon budget tells us how much is left, right? So if we go back, actually, the current estimate for how much carbon budget is left is shown on the right for 1.5 C, and this was for 2 years ago. This was through January 2021. This is 360 gigatons of CO2. Before we have a good chance of crossing 1.5 C. We've used up 2 years of that. That's 80 gigatons of CO2. So we only have about 280 gigatons of CO2, which is about 7 years of current emissions. Unless we really, really rapidly reduce our emissions, we will lock in 1.5 C of warming before the end of this decade. So just how small this carbon budget is the key point. And really why it upsets me when scientists and people that know better say that 1.5 C is still possible. In a world where people still do not cooperate on climate action, I think it's a really irresponsible thing to say. If we were all serious about climate action, if we were all working together on climate action, not competing on every aspect of trade and the energy system, then I think maybe we'd have a chance if we had started a few years ago. But today, the way the world is, we do not have a chance. So you have a carbon budget, so many hundreds of gigatons of CO2 left. So let's say the world comes together at a climate conference like will happen next week, and they say, okay, we can emit 1,000 more gigatons of CO2. That's a nice round number. Who is going to get to emit how much of those gigatons of CO2? And so that's where carbon emission allocations come into play. So this is from a review paper from a few years ago of different carbon dioxide emissions allocation rules. So basically it's that if you determine how big the pie is, you can then divvy the pie up in different ways. And so this is a sort of exhaustive list of the rules, but basically what they all are different versions of looking at GDP of your wealth, population, how many people are in your country, and historical emissions, how many emissions happened in the past as well. And so all of them are for the most part different plays on that, and those are different ways of doing it. Unsurprisingly, it's very complex, right? Different places might require different rules or demand different rules. And different rules are favorable to different emitters in different countries. And so this is just an explanation, for how complex it's going to be to divide up the remaining carbon emissions. So here's a really simple example of two rules for dividing up future carbon emissions. So this is from a paper from last year from South Korean researchers. And this is a really nice example. So they looked at a really strict carbon budget, a 100% chance of avoiding 2 degrees C warming starting in the year 2000. So one estimate for that was 745 gigatons of CO2 starting in the year 2000. And they looked at 2 rules. So on the left, EPC is equal per capita emissions allotment. And so basically what that does is it says that starting in the year 2000, every single citizen of a country gets the same amount of emissions. So you're kind of starting off in a very naive sense equally, right? And so basically you can see going down the EPC column, smaller countries get less to work with. They get a smaller carbon budget to work with, and bigger countries, the US and Japan, in particular China and India, they get more to work with because they have bigger populations, right? But what happens if you take fairness into account? What happens if you take historical emissions into account? That's what the right-hand graphic shows. And so this is a very strict fairness rule called historical equal per capita. And so what this rule says is that when all is said and done and everybody is done emitting carbon emissions, the average citizen of each country will have emitted on average the same amount of CO2. So this is getting the per capita amount of emissions equal over the lifespan of the fossil fuel economy. And basically what this shows is it shows just how badly historical emitters get hammered, right? These Western European countries, most of them have negative emissions. The UK has huge negative emissions. It goes from 6 to minus 48 gigatons. Canada goes to negative emissions, and the US goes to negative 200 gigatons, right? So we've emitted, and this is a reflection of the fact that we've emitted 500 gigatons of CO2 through the present, right? And, by fairness, we should not have emitted all of those. So this very, very strict rule says that we need to roll those emissions back to get ourselves in line with what other people are able to do. And then this shows that China and India are still modernizing, right? They show it's only been very recently that they've started burning fossil fuels and adding wealth to their country. So they get a huge allotment under this very strict rule. So this is an equal per capita, historical equal per capita rule. And you can see that it really punishes historical emitters. So there's lots of different ways to divide up future carbon emissions, and ones that take into account historical emissions and historical per capita emissions really, really punish countries like the US and the UK and a lot of European countries. And so the reason it does that is because of the major emitters, we have far and away the highest per capita emissions. And so that's what's shown in this Global Carbon Project graphic here. So this shows average emissions per person going back to 1960. And again, this is a data set that ends in 2020, so it has a big drop that was coming back. So there's a little V there. Imagine a little V at the end of those time series. And you can see that nobody comes close of the big emitting countries. Nobody comes close to the US in our per capita emissions. Nobody comes close to kind of our gluttonous use of energy, our gluttonous use of fossil fuels. The only major country that did come close was the Soviet Union, and you can see what happened when the Soviet Union collapsed and Russia fell into poverty in the 90s. Just this huge cliff of CO2 emissions per person as this enormous part of the world economy collapsed. If we look down below Russia and the US, we can see Japan has pretty high emissions per person, and China is getting close to Japan's per person emissions and has passed the EU's per person emissions. And the world average is about 4.5 tons per person. And India is well below the world average. So this is the kind of the fairness principle that determines a lot of rules about future carbon emissions, right? This fact that US per person emissions were so high, we got to build so much wealth off of all of those extremely high per person CO2 emissions, right? And so the really naive way to interpret this is that every country should get to emit as much as the US did per person, right? But of course, if that happened, it would be catastrophe, right? That would be so many CO2 emissions. So kind of getting other countries to get their share of emissions and getting our emissions down is the big ask of the next decades. Getting our emissions down, European countries' emissions down. And letting countries that didn't have as long of a runway in the fossil fuel economy, giving them a little bit more time to burn oil, gas, and coal. Because a naive reading of this just says that those developing countries, they get to emit as much as us. And if we do that, we'll blow through all climate targets. So key takeaways from this section: the biggest current emitter is China, but the biggest historical emitter, the emissions the climate system actually care about, is the United States. The US is going to hold the title of biggest emitter for decades, if not forever. There's a good chance that it's always going to be us in the end. So a key rule of carbon budgets, this way of dividing up future carbon emissions, is that there's less appetite for risk means a smaller budget. If you want to be riskier, you can emit more, but there's a good chance that the climate system is going to push you over the temperature threshold that you're looking for. There's many rules that have been proposed for dividing the remaining carbon budget, which attempt to balance population, fairness, and wealth, in addition to a few other things. And if historical emissions are taken into account, the US and many European countries used up their allotment of carbon decades ago, right? So if you look at historical emissions, they used up their emissions a long time ago. And the key point of comparison for fairness is emissions per capita. And if the US doesn't acknowledge that its shocking per person emissions are and were too high, then all of the developing countries that are rapidly growing their economies, they have every right to keep growing their emissions until they match our historical per capita emissions, right? Because that's what we did to build wealth. So everybody can do that, unless we acknowledge it and we work together for other ways for people to get wealth and a good quality of life. Something I touched on, but I think it's important to think about more than I was able to talk about, is that historical factors mean that for a lot of countries, their citizens probably are not responsible for the emissions that happen within their borders, right? If wealthy interests are the ones that cause the emissions and the local people got no wealth from it, they didn't really have a say in it happening, can you really blame them for the emissions? But I think for the case of the major fossil fuel consumers, specifically for people like the EU, for the US, for China, I think trade-adjusted country-level cumulative carbon emissions provide a very fair basis for portioning out blame, for apportioning culpability. I think it's a fair tool to use. For other ones where they may not be responsible for their own emissions, I think it's a more complex story to tell. But I think for the big emitters, I think these cumulative emissions are the key thing to look at. And all of this points to one thing: the US and most European countries literally cannot do enough to decarbonize themselves in the world. So what are some of the stories that America tells itself to avoid this responsibility? So the big story that we've been hearing for the last 6 weeks or so is that we're trying now. Look at this, Trump is gone. We have a climate president now. We're working really hard on our emissions now. We care a lot about climate. We're spending hundreds of billions of dollars over the next 10 years. Doesn't that show how much we care? And this graphic from Climate Action Tracker shows that that's kind of a lie, to say that we're trying hard. We're not really trying. So let's look at the left-hand side of this graphic. It shows U.S. historical emissions in black. And it shows where Climate Action Tracker thinks our current policies will get us in blue. And so it says that current policies and actions will reduce our emissions about 15% by the end of this decade. But they say their judgment of a 1.5C fair share is not negative emissions. It's not as harsh as the rule that I used before, but it says that we need to slash our emissions maybe 70% by the end of this decade. So a huge cut in emissions, and nowhere close to what we're going to do, we're projected to do, right? Again, this is just projected. It's not a rule that we're going to get that 15% reduction in emissions. So what Climate Action Tracker does is it judges the emissions, and it says kind of what world those emissions pathways could create if everybody followed a rule like that. And so if you look at this thermometer in the middle of the graphic here, the orange and the red, that's the line between 3C, below and above 3C. So our current policies are basically creating kind of a 3C world. That's sort of where we're headed. And if we wanted to do the 1.5C, the fair share world, it would be way bigger cut in emissions than what we're trying to do or projected to do. But a really nice thing that they include on here, so they call our climate action insufficient. I guess they want to be a little bit nice to us. When it was under Donald Trump, it was actually critically insufficient. I used the Wayback Machine and I looked at the last emissions, and it said that under Donald Trump, we were headed for a 4C world, and under Biden, we're headed for a 3C world. That's very dramatic. I don't think so, but I think they wanted to say something nice. But a nice thing that they do still include here is that climate finance, this far right-hand thing, is critically insufficient. And basically what that's saying is that we are not giving enough money to other countries to both prepare for climate change, to avoid climate change, and to pay them for the damages that we've caused, that our climate change has caused. And I think what this graphic summarizes is that American climate action is inward-looking and selfish, and it's really terrified of acknowledging the past. If we acknowledge the past, we would be sending more money abroad, right? We would be decarbonizing much, much faster because our historical emissions are so much higher. So the story we tell ourselves is that, we're finally trying, but in my opinion, we're not really trying yet. Another story we tell ourselves is that because we're spending so much money, because we're such an economic powerhouse, just by spending a lot of money, we're going to create an easier energy transition for the rest of the world. So this was a nice summary of this by this author on a project syndicate, and but I really have seen so many climate policy people echo this in lots of ways. So basically, what this author argues, what so many climate policy people argue, is that we're going to spend so much money, we're going to spend so much money on research, we're going to spend so much money buying clean tech stuff, that it's going to make it cheaper for everyone else to buy it when they need to buy it. And so this, if you know anything about the history of climate action, this is very similar to the argument that people make about Germany and the Energiewende, which in the early 2010s was a huge subsidy program for solar power in Germany. And it's credited with kind of giving a boost, if not a kind of a kickstart, to the Chinese solar industry, because Germany was willing to overpay for solar panels. And so the idea is that they were willing to pay really generously for the first generation of solar panels, and that allowed Chinese industry to learn very quickly how to reduce solar panel prices to where they're very low today. But I think the idea is that we're going to get to do that, but with all kinds of clean tech things. Personally, I find that really offensive to say that these really soft things can be accredited to us, especially when the climate law has no hard fossil fuel phase outs, no explicit climate aid, and those things I think are the hard core of real climate action. Is a year when you say you're going to stop burning fossil fuels, and explicit amounts of money to the people that are going to suffer the most. I really think that the Inflation Reduction Act is much more about energy security and competition with China than it is about climate action. And I think that'll become more and more apparent over the coming months and years. Another story we tell ourselves, a really evil story, is that it's okay if the United States makes a little bit more money off of oil and gas for the next 30, 40 and longer years into the future. So this is a graphic from the EIA, the Energy Information Administration. And it shows the capacity of liquefied natural gas export facilities in the United States and ones that are going to be added in the next couple of years. And so it seems like in the next few years, we'll be able to export about 20 billion cubic feet per day of liquefied natural gas from these export facilities. And the really nasty thing about this is that this is actually considered climate action in a lot of ways. So a big way that we lowered our carbon emissions over the 2010s is this explosion in fracking and this increase in natural gas. And so natural gas got so cheap that we retooled coal plants to burn natural gas. And that, on a per energy basis, has lower CO2 emissions. It often has higher methane emissions, especially if you count upstream links. But if you just talk about CO2, the natural gas is much better. So the idea then is that the developing world is going to follow the same pathway as us, right? So when EU starts using less LNG after this energy crisis is over in 5 years or so, after the US is using less natural gas, the US LNG industry, is going to be able to sell to Asia, to economies like China or India or Indonesia, places that are dependent on coal right now. And the idea is that it'll reduce carbon emissions, right? So it'll be climate action. So we get to make money off fossil fuels, and we get to say that we're helping these countries decarbonize. And so one of the ways this is really nasty as well is that under the Paris Agreement, exports are not counted against a country's climate target. So the US could technically be net zero even as we're exporting millions of barrels of oil and billions of feet of cubic feet of gas per day. So under the Paris Agreement, we could be net zero and still be an enormous fossil fuel exporter. So this is a really goofy thing, and there's specific things in the Inflation Reduction Act that actually are supposed to make oil and gas cleaner. They're supposed to plug leaks from things like methane, and so that means that we can advertise that our oil and gas is cleaner than places like the tar sands or Russia, places where it takes a lot of energy to create energy. So if we can have cleaner oil and gas, that's another reason why oil and gas can be a climate friend instead of a foe under this story that kind of we tell ourselves. A last story that we tell ourselves is that, it's not our fault that we burn so much. And this is sort of one way that I think that story gets told. So this is a graphic from Exxon Climate Science Research. So before the early 1980s, Exxon had a really good climate science research program. They had really state-of-the-art climate models and climate scientists that were at the cutting edge. And this graphic is a demonstration of that. So what they did was they looked at warming across the globe under a doubling or a tripling of CO2 or a halving of CO2, so CO2 relative abundance to pre-industrial. And if we go to the 2.0 on the x-axis and you go up to the solid line, the first solid line, a doubling of CO2 under Exxon's model that's 40 years old gives you a warming of about 3C. And the current best estimate from IPCC models is about 2.5 to 4C. So the Exxon model is right in the middle of that estimate. So Exxon model 40 years ago was about as good as kind of the broad aspects of the most modern cutting edge climate models. If you talk to a climate old head, they'll tell you that climate models in some ways have failed to improve on the original climate models, even from the 60s and 70s. And this is one demonstration of that, is that they still give pretty good estimates of warming, even though they're much less complex. So this is this really neat thing, right? Like Exxon had this amazing climate science research program, cutting edge, but heading towards the late 80s, Exxon realized that climate change kind of hurt their business model, right? Or acknowledging climate change hurt their business model. So they flipped over to very hard denier mode delegitimizing science, paying scientists that were willing to lie, paying politicians that were happy to spout nonsense. And that's had disastrous consequences for us today, right? That denial is still with us today. That was in large part funded by groups like Exxon. My question, though, is if you're on the international stage, if you're negotiating on the international stage, is a country that is going to be destroyed by sea level rise, is it going to care that you were lied to by Exxon, right? Exxon is a U.S. corporation. Is our responsibility divorced from corporations that are based in the U.S.? It was our job, to keep them in control. That's the job of the country where the corporation is based, right? I do not think on the international stage our responsibility is divorced from the responsibility of corporations. I don't think we can point the finger at Exxon. It's a very important reason for how we got to today, but I don't think it removes blame from the U.S. as an entity because it is a U.S. corporation. I don't think it gets us not a get out of jail free card, which is, I feel like, how some people treat it. So one last section here, just about 10 minutes or so. Learning all that climate science. I hope that this kind of helps us set the stage for next week in negotiations at this climate conference, and really all climate conferences to come, all climate treaties, all climate negotiations to come. So let's kind of set the stage for where we are today. So under the Paris Agreement, developed countries promised $100 billion a year in aid to developing countries. And this graphic shows just how far short most developed countries are in providing that aid. So this is relative to fair share. So in the middle is 100% of your fair share. And you can see that some countries have actually given more than their fair share to this $100 billion a year finance vehicle. Countries like France and Japan, Norway and Germany. But countries like Canada, Australia, and especially the United States are paying nowhere near their fair share, right? Well below their fair share, well below the 100% as shown on this graphic. The funding, the last I've seen, the best estimate I've seen is that the generous estimate is that 80 billion of 100 billion has been handed out in the last couple of years, but before that it was far short. The problem with this is that it's reported by the developed countries, so they can say that they sent it out. That's the current way that it's reported. And receiving countries say that these numbers are a huge exaggeration, that they do not receive nearly this much money. So there's a lot of wiggle room and a lot of room for lying. Another thing that I find very insidious here is that most of the money here is in the form of grants. Or in the form of loans, not grants. So it's giving countries debt instead of just giving countries money. And so I don't find that to be particularly compelling form of climate aid. And so in a lot of ways, we're falling short. Developed countries, especially the U.S., we're falling short on giving money to developing countries. And even if we did hit those goals 100%, it's not clear if it's in the most helpful form. So that $100 billion a year in climate aid is meant to help developing countries with adaptation, preparing for the warmer future, and with mitigation, with moving into the post-fossil fuel economy. What it does not do is it does not pay for damages from climate destruction. And so that is a whole separate category, and it's called loss and damage. And so an example of loss and damage are these horrible floods that happened in Pakistan this summer, when the rains just would not end, and so much of Pakistan was underwater. So this is from the WMO, from a rapid attribution study. And what this study said was that climate change may have increased peak rainfall about 50% during the Pakistan floods this summer. And those floods, latest estimate I saw was possibly more than $40 billion in damages. That honestly seems like an underestimate to me. And so, if it caused that much in damages, and if a significant part of the rainfall was made worse by climate change, that means that a significant amount of the damage was done by historical emitter countries, right? If present day warming is responsible for those floods, for a large part of those floods, then historical high emitters should be the ones that pay for those damages, right? And so this is an example of loss and damage, which is destruction by climate change, very different from the climate funding that's described in the previous slide. And I think attribution science like that's discussed in this study is going to be very important to determining loss and damage. How much worse was this hurricane? How much worse was this monsoon? How much worse was this drought because of climate change? How much more damage did it do because of climate change? This science, it's very young. There's not many people that do it. There's really only one group that does this rapid attribution. And I think problematically, they're based in Europe. I think that's something that should be based in many places across the world, so there's comparison between them. But I think it's going to be a really important thing going forward. So loss and damage is destruction by climate change, this thing that's destroyed. And it's split into economic loss and damage, like the loss of a home or the loss of a harvest, property destruction, something you could put a number on, I guess, if you're cold-blooded. And non-economic damages, loss of an entire way of living, loss of the country where you live if you're a low-lying island nation, right? I mean, how do you put a monetary value on the loss of the place that you've always lived? And the only Western governments that have given symbolic loss and damage money are Scotland, which happened last year. Belgium's Wallonia region, so only one of the main 3 regions of Belgium, and that happened after Scotland. And then the third country was Denmark. And those 3 countries together, it's only a symbolic amount of money. It's only $15 million. But the reason why it's an important milestone is that loss and damage money specifically admits culpability for climate damages, and that's distinct from other climate funding, right? So they've only really started the conversation, but it's very important that they've kind of opened the door on that. And a big reason why it hasn't happened is that the U.S. and other high emitting countries have blocked loss and damage provisions at all previous climate negotiations. Just a long history of blocking loss and damage from being explicitly funded, explicitly acknowledged. And you can see the reason why they do, because the U.S. is scared of the past, right? If every single climate event that happens in the future, if you say it was made X% worse by climate change, the biggest finger that is going to point back, at someone is going to be at the U.S., right? Every future climate damage for the next 30 years, possibly for the next forever, is always going to point at the United States, right? And so this attribution science, combined with economic estimates of loss and damage, is going to kind of tell the tale of just how much money we should be giving to these countries that are suffering the effects of the emissions that we put into the air. So this is going to be a really big thing at this next climate conference next week, and a big reason is because of these floods in Pakistan. So they want us to give explicit loss and damage provisions in international climate law, ones that are funded explicitly, and help these countries that are going to take the brunt of climate damages going forward. So one last summary slide. The science of blame, as the floods and droughts, heat waves and famines make places unlivable, carbon accounting, like I've laid out here, is always going to provide the most straightforward way to apportion blame, looking at cumulative carbon budgets. The climate system, because the ocean is slow, it cares about carbon emissions from 200 years ago as much as from 100 years ago, as much as from today. And these cumulative carbon emissions are the best way to lay out blame for all the damages to come. I argue that historically high emitting countries literally cannot decarbonize fast enough. They should have decarbonized 20 or 30 years ago. And low-emitting countries have every right to demand, bankrupting levels of mitigation and adaptation aid, as well as this loss and damage money, this explicit payment for climate damages from the historical high emitters. And one of the things, that worries me about this is that the longer historical high emitters like the U.S. refuse to acknowledge the past and refuse to act, the more suffering the world will lock in. And I think the closer we get to a complete collapse in cooperation on climate action. And I think a really big thing standing in the way is acknowledging past emissions, acknowledging that a lot of the damages today are from past emissions and they're from high emitters like European countries and the US, and of course, increasingly China. And I think this unwillingness to acknowledge past emissions from places like the US in particular are just a huge roadblock standing in the way of genuine climate progress. And I think if we can't acknowledge those emissions, we'll have this schism in international politics, where one side, points the finger at us rightfully, and we say, oh, we didn't know, or we deserve to, or it's our right to have admitted all those things. And those two sides will never be able to come to agreement, and we'll never ever, get to global net zero if those two sides. And I think a key thing is getting the U.S. to admit culpability, places like the U.S., historical high emitters. So thank you to my Patreon subscribers. I would not have made this without them. I wouldn't. And my Patreon is HK81. It's mostly a monthly newsletter of my thoughts on current stuff going on in climate science and climate action, and updates on projects that I'm working on. There's a link to my slides in the video description. Ask me if you want any of the references here, if you can't find a PDF, or if you want me to dig up something, a specific figure I found. I'm happy to answer questions. Just leave a comment or find me online. Thank you, everybody.